All right. I think we might have some folks coming in a little after the hour here, but I'd just like to get started with some of kind of the logistics of the webinar format here today, some kind of housekeeping type stuff before introducing our speaker. So first of all, just if everyone could please keep their video function off throughout the webinar. There'll be opportunities at the end during our question and answer where we can turn that back on, but just to conserve bandwidth and make sure that the streaming and kind of the clarity of the image is crisp, it'd be helpful if everyone could keep their video off and their microphones muted until there's opportunities for question and answer. And I will let you know when it is time to turn off your microphone. I can call on you. That said, if you have questions throughout the webinar, please, we'd love to have those questions. Please enter those into the chat function. It's in the bar at the bottom of the screen here. You can see it like a little speech bubble there. If you click on that and add your question in there, I will keep track of that question. And then when there's a break in the webinar, Jan Willem will open it up to questions and I can share your question with him and open up a dialogue between you and Jan Willem. There's going to be some interactive components to today's webinar. And so Jan Willem will help us kind of figure out the functionality of that, but he's basically going to be asking, your opinion on some different issues. And I'd like it if you entered your response in the chat box, and then again, I will relay that to Jan Willem. If you missed the very beginning here, just please sign into the chat box with your name, affiliation, where you're from, and if you'd like your contact information, that would be great. We can send you the recordings and other information about future webinars. There will be an in-depth question and answer period at the end, and I think one about halfway through as kind of a bathroom break, so that people need to get up for about 5 minutes. We can do some question and answer there as well. That's kind of the housekeeping bit. So without further ado, I'd like to introduce our speaker, Jan Willem Janssens, who is the owner of Ecotone Landscape Planning. As I said already, this is the second webinar of the series exploring soil health in pinyon juniper woodlands. And we're really happy that you could make it today. This webinar is in collaboration with the Forest Stewards Guild, which I work with, and with support from the New Mexico Department of Agriculture and their Healthy Soil program. So really happy to share this information with you. I'm very excited about having this information myself, working with the Guild. And so just wanted to pass it over to Jan Willem Janssens. Thank you all.
Thank you, Gabe. And thank you all for joining today. I'm very excited to do this second webinar, and grateful for the support we received from the New Mexico Department of Agriculture's Soil Health Program and Forest Stewards Guild and Glorieta Freedom Ranch, which are indispensable in making this webinar series possible. For those who don't know me, I come to this webinar and this topic as a landscape planner and a forest ecologist. I have a degree in landscape architecture from the Netherlands, and have been working in northern New Mexico for the last 27 years with a focus on watershed restoration and forest and woodland management and land use planning in general. I actually used to work for the precursor of the Forest Stewards Guild when it was called the Forest Trust. And so I have a long relationship with the place where Gabe is coming from, and I'm still an ongoing professional forester and member and partner of that organization, actually, and consultant. So it is a joy to continue that relationship in this way. Soil health has been an interest of mine throughout my career here, because I've been focusing a lot on the relationships between forestry and watershed conditions, soil and water health conditions. And so that is actually at the center of a lot of my work, basically the interaction between forests and plants and water, and therefore you have to look at the soil, and that's actually how I came to this specific topic. Now, with that, let's go into this webinar. The webinar, like the previous one too, introduces the critical importance of soil in holding water and as the natural growing medium for plants and many other forms of life. I will explain a little bit about the self-generating and self-healing capacity of soil. And that's particularly possible if the soil is not overstressed. We'll see again how soil is a living ecosystem that we need to really take care of with attention and dedication in order to allow it to come to its fullest potential of harvesting and storing water and supporting plants and other life, and providing the many services that we often have taken for granted. For instance, in pinon juniper ecosystems, maintaining soil health contributes to enhanced grass cover, tree health and vigor, and as a result of that, we may expect better wildlife and livestock forage conditions, pinon nut crops, firewood supplies, and for instance, wildlife habitat. And we've definitely seen those conditions improve on Glorieta Freedom Ranch. And as a result of that, we may also expect greater tree resilience and drought and insect and resilience during drought and insect outbreaks. So Gabe has explained already about the logistics, so I think I can move on. If you have any questions about this, use the private chat box to contact Gabe, and then he will probably give you pointers if you're in trouble and help you connect or understand how this works. So we're going to focus today on measuring woodland and soil health. And the key question is, how can we measure and evaluate woodland soil health? And I want to amend that by saying, so that we have at least qualitative information and also some quantitative data to make sound management decisions. And it's those management decisions and solutions that we're going to address in the next webinar that will take place in 2 weeks. Although we're going to take a little sneak peek of that because I will address some of those management possibilities in this webinar as well in relation to the findings that we're going to practice in the monitoring work. So we're starting this webinar with a little overview of the study area again, so that those of you who have not been part of the first webinar have a sense of what this area is that we're focusing on as a target or study area, and what different types of pinon juniper ecologies exist there. And we're focusing also on what soil really is and how soil is an entirely separate ecosystem in itself. We will review again the 5 healthy soil principles, and at that point have a brief break for questions and answers. And then we're getting into the meat of all this, for which this introduction is really important, especially if you haven't followed the first webinar, because we're going to focus on what erosion is, what the definitions of erosion are, how you can actually observe erosion in the landscape, and how we can actually measure or qualitatively interpret and analyze the landscape with the Bullseye method, both for grasslands and woodlands, and also look at a method for soil loss estimations in forest and woodlands that gives more quantitative background information. And then we'll summarize the monitoring exercises with a review of some possible management options, and then end with questions and answers. So where are we doing all this work? I've had the pleasure to work with Brad and Kathy Holian for the last 10 years or so on their property, Glorieta Freedom Ranch, located on Glorieta Mesa. The Glorieta Freedom Ranch is a forest and woodland property about 25 miles southeast of Santa Fe. It's part of the Ranch at Powder Springs subdivision. And the area is located in the southwestern corner of the former Pecos Pueblo grant. The property is surrounded on the north, east, and south by private land, and on the western side by Santa Fe National Forest land, as you can see a little bit on the map to the left of you here in this image. And there is some national forest on the southeastern corner as well. The shape of this property includes multiple parcels and spreads across approximately 870 acres and has elevations ranging between 8,000 feet on the flanks of Cerro de las Escobas, which is on the far left side, on the east side of the ranch, meaning the right side in this image, and about 7,300 feet at the valley bottom of the southeastern side of the ranch. So in here are Brad and Kathy, and the ranch is managed as a tree farm. It has a history of homesteading, grazing, and woodcutting. And in the past 50 years, the ranch has been managed for conservation purposes and underwent a series of ecological restoration and stewardship activities. The ranch is also very much used as a stewardship education and research site for regional conservation groups, educational institutions, and as of the last year, also Pueblo Mesa is very interested in participating. And so that is the summary and background of the area where a lot of the background research that I've done is focused. And we chose this area because it has such a beautiful diversity of forest lands in relation to the diversity of soils. And we have also a lot of different techniques to show, especially in the next webinar, of different land management practices. And we have a history of monitoring of the last 10 years with a baseline. So there are very few properties that offer this continuous type of monitoring and monitoring also of the land restoration effects. And that's why this is such an excellent opportunity to share from in this webinar series. Again, for those who have not participated last time, I want to very quickly go through the different types of pinon juniper ecosystems that exist and that you can find on the Glorieta Freedom Range. Here particularly, we find persistent woodlands and a subset of that called open woodlands. They are dominated by winter and summer precipitation, are located on somewhat coarser grained sediments or soil types, sometimes even rocky, and have a pretty long-term fire frequency. So the natural fire frequency of persistent woodlands runs into hundreds of years. Then we have ponderosa pine stands, sometimes mixed with pinon juniper understory. And it is not quite clear from research, either here or in other locations, whether that is a transition or actually an ecosystem in itself. Here and there, we get the impression that it might be its own ecosystem in the sense that there are really no fire history signs, and that you find old trees of hundreds of years old, both in the pinon and in the ponderosa, while the ponderosa typically has a fire cycle that is repeating within a couple of decades. You would expect that there is a fire history here, but there really isn't. So, and we don't know the fire history actually on the ranch very well, and that will require some more research. But at least a fire and ponderosa and pinon ecosystem might actually be its own type. Then we have alluvial fans with grasses and forbs and some mixed vegetation, often a Rocky Mountain juniper, and typically a lot of the different types of species that we find on this landscape. There are also wetlands and riparian areas, mostly in the drainages, like of the Padua Springs, and valley bottom grasslands with scattered junipers, mostly Rocky Mountain juniper, but also encroachment of ponderosa pine and piñons. And they all are related to specific soils, and we're going to talk about those next. So here are the soil types that we find, and they're numbered in relation to the soil survey for the area. So type 702 are fine sandy loam soils in the valley bottoms, typically those grassland valley bottoms that are dominated by grasses and forbs, and as I said, Rocky Mountain juniper. Forest type soil type 703 is typically a rockier soil with fine sandy loam that is very shallowly covering the rock material. And the landscape type is arroyos and alluvial fans. And here you find ponderosa pine, Rocky Mountain juniper, piñons, and grasses. The bedrock can be as deep as 122 inches, so it can be actually very deep, but in some areas it's very shallow as well. 705 is clay loam and loam soil with deeper down calcium carbonate layer that actually confines the groundwater table. And so it is a pretty dry type, also because it's often a sloped landscape. We find piñon, Guanxi juniper, and oak, and it is located on Mesa slopes and shoulders in the landscape, and in this specific property on north-facing slopes. Soil type 707 is one that is dominated by sandy loam and is on the lower slopes. It dominates more than half of the range and its landscape, and grows piñons, junipers, oaks, and grass, and has many openings that are partly natural and partly created by woodcutting in the past. Another important and dominant soil type is 708, which is a clay loam type, so slightly finer than the 707. And it has piñon, juniper, oak, and some grass, and is more on the foot slopes, where actually the sediment flows out more than on the lower slope part, and therefore you get a finer texture of soil. There is also a type of 708 that is on plateau shoulders. It's more cobbly loam and fine sand, and it has more ponderosa pine besides piñon, juniper, and grass. In the 708 soil type, the bedrock is much more shallow. It is between 7 and 17 inches for the foot slopes, and between 20 and 30 inches for the plateau shoulders. So that creates drought conditions here and there that generate openings, or situations where ponderosa pine actually thrives well, but other vegetation doesn't thrive so well. So after that introduction about the area, I want to focus a little bit on the soil and what soil really is. I've chosen a definition from the Natural Resources Conservation Service, and this is the definition, and there are many actually, but this is most beneficial for our focus of soil health. Soil is a natural body comprised of solids, minerals and organic matter, liquid and gases, that occurs on the land surface, occupies space, and is characterized by one or both of the following: horizons or layers that are distinguishable from the initial material as a result of additions, losses, transfers, and transformations of energy and matter, or the ability to support rooted plants in a natural environment. So here with this graph, I want to show what that really means, because it means that soil actually is happening And I say happening, but because it's really a process almost more than a status, a situation. It is happening in the intersection of atmosphere, the biosphere, the lithosphere, and hydrosphere. So that means that gases and heat from the atmosphere are mixing with water from the hydrosphere, living organisms from the biosphere, and mineral material from the lithosphere. And so then there are the outside elements or forces from time, topography, which is largely also gravity, and people's activities that then work on those different spheres and kind of fuel that process that leads then to the soil environment or pedosphere. And it's really essential that these both the contributing elements and the processes contributed by each of those spheres are in balance with each other to really form soil and to continue to form soil. If there is a lack of balance, then the process of soil formation will stop and soil will gradually degrade. And the degradation of soil is, of course, an unhealthy situation for soil. So there, the entire idea of soil health comes in. So soil health actually means the balance between those different spheres. So if we take a snapshot of soil, and I'm sorry for this grainy picture, but I didn't find a better one, we see that actually the soil consists for nearly half of solid matter, inorganic mineral matter, which is about 45% or more, and organic matter, consisting of microorganisms and macroorganisms, up to about 5%. In enhanced forest soils or agricultural soils, it might be a little more, but this is pretty much what you'll find. And then water and air comprise the other 50%, but they're much more variable. And you can imagine that because if a soil is dry or the water table is very deep, like in many places right now in New Mexico, the water content is much smaller, can drop to maybe 5% in sandy and gravelly soils. And then the air will fill all the voids or the pores and will grow beyond 25% to maybe 45%. But in healthy soils, it's more balanced in the order of 25% for water and air. So how is then soil different from rock or dirt? Well, rock or dirt is pretty much just mineral content, right? It doesn't have the organic matter component. It has very little water or air, unless it's dirt that's unconsolidated, then it may have some water and air in it, but we'll see soon enough that just dirt by itself doesn't have a high capacity of holding water. So soil, therefore, is a complete ecosystem. It's alive, and that's pretty much thanks to the organic matter in the soil. And as a result of its living characteristic, the live components and all the interactions that are happening between the different spheres that I mentioned lead to mutualistic relationships, symbiotic relationships, and competition between the various organisms. And it's located only and exclusively in the upper part of Earth's surface, within that mineral matrix, that mineral environment that is part of the much deeper Earth. And it is stratified in layers, and the proportional amount of the living biomass versus the area without life, that means the organic versus the mineral material in the soil, that defines those specific layers, and the layering and its colors define the different types of soils. And the layering, I mean the thickness of the layers, the amount of organic matter, the color, which represents part of the ionization that's happening in the soil, etc. And so we have many different soils that can be classified, and that's in itself an entire science and of great interest. that reminds me now, actually, the soil science museum where this all was first classified about 100 years ago is in my alma mater town of Wageningen in the Netherlands. It's the International Soil Classification and Research Center, ISRC, that's part of an international network of agricultural research stations all around the world. And it was very fun to go visit that center because they have soil profiles from Siberia, from here in the Western United States, from the Andes, from Africa. And so you can see soil profiles with their different colors and names from all over the world. It's totally fascinating. So here is a sample soil profile where you can see the different coloring and the different layers. The top of the soil is called the O horizon, related to the organic zone, plant litter zone. Then below it, you have the A horizon, the surface zone, or together O and A are the topsoil that have a lot of organic matter. They're also called the upper soil, and they have the highest level of biological activity. And they pretty much characterize a lot of the soil fertility components and water holding and infiltration characteristics that are so important for healthy soils. Then we get into the B horizon, which is the root zone, and where only organic matter conversions take place associated with the root channels that run through the soil. Here we will see a higher level of, higher percentage, you could say, of mineralized carbon in the soil. And that leads then also deeper down to the level of the C horizon, where in the C1 horizon, you still have roots in the parent material, but where you identify a C2 horizon, where the mineral components are fractured, but no longer is there any biotic plant material present. And then below that, the R horizon, which is just the parent rock material. The B and C1 horizon are called the lower soil and are characterized by biological activity and but by increasing geological and hydrological functions and material. And then in the no soil component of C2 and R, we have no biological activity and mostly exclusively parent rock material. That's important to consider because that tells us something about water holding capacity and the possibilities for life development in the soil. Here in this overview, which is a critical concept of understanding soil health problems, especially in sedimentary soils or soils with very little organic matter, it tells something about where and how soils hold water. Water is retained in the voids, in the pores, through capillary forces, which we know in daily life as the force of wicking, and osmotic forces, which is the water adherence to molecules or ions. And together, they're called the matrix suction, and the forces in the matrix of the mineral soil. After soil has been saturated, part of the water drains out of the pores under the influence of gravity, and part of the water evaporates through the top of the soil, and then the pores open up. The moment at which the force of gravity and evaporation is the same as the capillary and osmotic suction, drainage will stop, and evaporation stops too. And at this point, the relative water availability in the soil is called to be at field capacity. So at this point, water only adheres to the outer layers of the grains of the particles, the mineral particles. And only plants have a little bit of potential, depending on the plant and the amount of suction that's happening in the particles, to take some water off for their own uses. So, and if plants continue to need water beyond the point that they have reached their maximum suction, they will wilt. And therefore, this point of exceeding of suction exceeding in the mineral matrix beyond the suction power of the plant is called the wilting point. And of course, areas that have, or soil that is coarse, have a moderate to high porosity and high permeability. Clay particles and silt particles have a high porosity with low permeability, and they have a high relative surface to hold water on their surfaces. So they have a much higher capacity to hold water at field capacity up to 25 or 35%, whereas sand grains have maybe that capacity up to 5%. So that gives you the indication as to how plants have a greater possibility to take water up from clay particles, but clay particles also have a higher matrix suction, so hold that water stronger. And so it is a balancing act as to how much plants can suck water from the soil. And typically in loamy clay soils, that's optimal for plants. Sand drains that water away too quickly, and the pores are actually too small for roots to take hold. So sandy sediment soils are not optimal growing environments, and they have to be adapted to really be good growing grounds for plant regeneration. So the question is then, how can we improve soil structure to make that water hold more water, the soil hold more water, and then also provide more plant growth? Well, you might think just add water, right? No, not yet. First, we need to add organic matter and life forms. And that is because what life forms create an organic matter, greater diversity of pore sizes and in all directions into the soil. And the mixing of organic matter throughout soil horizons really helps eventually just with increasing the water holding capacity at greater depth and throughout the soil. And that leads then eventually to optimal root penetration at greater depth, more life forms and biological activity that then actually help with humification, which is the process of breakdown of organic matter to a stable carbon component, which is known as humus, besides the mineralized carbon that chemically adheres to minerals. And then you get increased ion exudates from the biochemical soil activity from microbes, and this increased ion exudate holds the soil better together, and it's then also available for plants as critical building blocks and germination hormones, you could say, and is essential for plant growth and plant establishment. And then eventually, once all those conditions are in place, water retention is much more diverse throughout the soil structure, and all the pores are better connected. You have greater diversity of pores and multiple ions made available that also in turn can hold water, and water then in turn transports those ions to fungi tips that are associated with the rootlets that then transport them to the plants, and then you have a much more productive soil structure and soil ecology. So what's then essential about soil science today? That it is really, we have discovered that soil is really alive. That from an ecological perspective, it is an ecosystem and a microbiome with countless microorganisms, including bacteria, fungi, protozoa, nematodes, worms, insects. And in fact, there are billions of soil microbes in just a teaspoon. And that gives you the idea of how important and how alive a healthy soil really is. And that these interactions between all those forms of life and all those different spheres that are coming together in a healthy soil create that process of soil formation. And those exchanges that are essential for continuing to build the soil and supporting all the functions that soil provides for the life above ground. So what's then happening in relation to soil science in pinyon juniper woodlands and savannas? Well, it's a field that's still very much in movement, you could say. There's still much being discovered. Effectively, actually, just last month, issue of the Society of Ecological Restoration's journal, I think it's called Ecological Restoration, has an entire issue focusing on soil research in relation to above ground woodlands, forests, and above ground ecosystems, and how those relationships actually take place and how land management influences soil health and how soil health improvements support healthier terrestrial ecosystems. We do know that root-associated microbiota, especially root-associated fungi, are essential for above-ground life, and that there are very specific relationships between those fungi and the health of ecosystems above ground. We have found also in the literature or scientific studies have found that sufficient tree density and ground cover are important factors for soil health and for what is called eco-hydrologic resilience, a term coined by Richard Miller in a pretty important research paper on PJ woodlands and savannas throughout the west of the United States. We know that there is carbon accumulation in plants, litter, soil, organic matter, and microbes, and that in our various landscapes, pinyon juniper woodlands are so important that the carbon accumulation in all these different forms may actually be very important across the landscape of the West, meaning that proportionally pinyon juniper woodlands are very important as a carbon sequestration ecosystem. And mineral carbon sequestration results from plant growth and soil microbial activity particularly. We've also learned in the last decade or so that biocrusts should not be overlooked because they sequester carbon, although in a little bit, but they also, very importantly, maintain soil structure and prevent soils from eroding. And various types of carbon and their sequestration rates depend on stem density, tree age and size, and the sizes of woodland openings. And if we make those openings too big and reduce the stem density, then we'll definitely decrease carbon sequestration rates. So to sum it all up, soil health is therefore related to all the different spheres here and their products and the processes that they contribute to in the soil, so that eventually the soil as a process contributes stable organic compounds and leads to the continuous biochemical conversion of all the products contributed by those different spheres. And that's really essential to understand. It's really a process-driven understanding of soil health. So now that we are understanding maybe a little bit more about soil and soil health, you may wonder, what is then a soil that turns unhealthy, right? What degrades soil? Well, it's typically a certain amount of stressors that naturally occur or that are occurring in relation to past activities or in relation to current stressors. So natural stressors are for instance, drought and fire, flooding, or slope and geology, gravity-driven processes like erosion. The images at the top here indicate those. Then there are legacy stressors, stressors that are based on ongoing effects, impacts from past activities, such as grazing, which may have depleted plants and soils to the point that it's been taking 100 years or more now for that land to stabilize and for soil to regain health. And in fact, still in many places here in New Mexico, erosion and other aspects that are called brittleness of the environment are continuing. So those soils and environments are so teetering on the edge of being balanced that they're easily tipped back into a degrading situation. Dryland farming history is an example of that. And of course, there are many places where there is water extraction and where the soil is unnaturally too dry, either as a result of water extraction from wells or as a result of gullies that are extracting the water as a result of gravity that sucks the water to the lowest point in that gully, and that makes that these perching grasslands next to gullies are drying out too quickly. And I'm giving that example because many gullies are the result of cattle tracks, wagon wheel tracks, or land development that has caused those gullies to develop over the last 150 years. And then there are current stressors, such as land clearing for parking lots, baseball fields, clearing for development, and then the big problem of all-terrain vehicles and off-road vehicles, of which we have definitely seen an enormous rise over the last several decades. Ongoing farming that causes land to be fallow, construction in which and our regulations that allow construction sites to remain fallow, especially during times of rain and wind, and then many dirt roads. So let's look at this a little bit more in detail. Why is soil health structurally declining? Structurally in the sense of that the soil is really falling apart and eroding. Well, one of them is atmospheric extremes like heat and the energy of the sun, wind, etc. Then we have soil moisture imbalances. We create dry spots, wet spots, and then you get that under the influence of the atmospheric extremes, certain dry spots on top of the past disturbances and stressors that they've experienced create bare spots, and these bare spots become more and more connected and become drier and drier as they evaporate water from the surface more rapidly. Then there are intensive human uses and activities such as cattle trailing and tire tracks, and all ones that I've just mentioned before. And then that leads to poor plant growth to hold that soil together and to create the biological activity and carbon in the soil that holds it together. And then eventually it starts running off and you create these perched soils that I just mentioned that are drying out more rapidly and that eventually are being undermined. And then you have major erosion happening. So how can we keep our soils healthy? Well, a healthy soil, as defined by the New Mexico Healthy Soil Act, is a soil that enhances its continuing capacity to function as a biological system. It increases its organic matter and improves its structure and water and its nutrient holding capacity. And scientists here in New Mexico and nationwide have summarized principles for maintaining soil health in 5 categories. And it's a very clever system that we might want to keep in mind, and that is really helpful in checking and monitoring soil health in various situations. And these principles, and when we implement each of those principles, or all of them, it helps keep soils healthy in many different environments. It maintains optimal soil structure. It maintains self-healing capacity of the soils after being exposed to stresses, and sustains the biological functions. So let's go through them, because I didn't have a lot of chance in the first webinar to look at them in more detail. Soil cover is the first principle, and it relates to the presence of living plants and of organic mineral mulches such as plant litter, woody debris, and stone material. And how do you think that these cover materials keep soil healthy? Well, think of a protective skin, right? Think of the exchange of cycling of minerals from that cover that we put in there, and then the breakdown of it and its penetration into the soil. Think of how it helps with water retention, especially if that cover isn't too dense, because then water is expelled by the terpenes in, for instance, conifer branches or wood that's spread out. But if there is some bare dirt visible, then that water will infiltrate, but the shade from the plants and the mulch will actually cool down the soil and prevent evaporative losses. Think of the growing medium that these mulches provide and the cover, or the habitat for plants and animals and their interaction with the soil. The second is minimizing soil disturbance and external inputs. This is particularly important on croplands, but also applies to rangelands and forests. We want to disturb the soils as minimally as possible by wheels or anything that removes that cover that I talked about, and especially the biological activities that happen below them in the topsoil. And we don't want to remove at all, of course, any organic part of the soil. External inputs are also mostly applicable to croplands, because there we think about adding fertilizers, fungicides, herbicides, and pesticides. And you don't want to do that on rangelands either, because it impacts the biological life of soil to the point that actually we're setting back the clock in the soil's self-development process. The third principle is that of maximizing biodiversity, and that relates to the multitude of diverse life forms above ground and below ground that interact with each other, and that help the soil survive, rejuvenate, and be resilient. And it relates to also all the microorganisms in the soil, the mycelium, and especially the mycorrhizal fungi that are connected to the rootlets, and the bacteria that are connected to the life of the fungi, and the breakdown processes that happen in that environment, and that are essential for mineral exchanges and for carbon buildup in the soil. The fourth principle is that maintaining of a living root. It relates to plants that are above ground and connected to those roots, of course, and those plants that photosynthesize above ground and contribute to the carbon exchanges in the soil, because it's through the photosynthesis that actually carbon is stored in the soil. And because fungi feed on the carbon that is actually brought into the soil, and the bacteria that have carbon in their bodies break down, and also the skeletons of the bacteria eventually contribute carbon, so that that carbon is then further stored, enriches that soil, provides again food for other organisms in the soil, so that you get an entire cycling system of carbon that then helps to hold water and improves that soil structure that I have mentioned before. And especially when that soil structure is really deep, helped by the roots. And I explained earlier how root penetration in the deeper subsoil is so essential, because that can only happen when there is space, when there is water, when there is carbon, and when there are microbes to actually create the space for those roots and the mutualistic symbiotic environment in which those roots can grow and then take up that water again for the plant. So it's a total interactive system between the photosynthesis above, explained here in the right-hand side by this 400-year or more pinon, and the soil where all these microscopic activities are happening that are, that you can really see almost only by the health of the tree above ground. And then finally, the other fifth principle, healthy soil principle, is that of including animals. And that could be livestock, wildlife, small soil organisms, and all related to soil health in their natural interactions with the soil. And how do you think the various animals keep the soil healthy? Well, think of the excrement, for instance, the breakdown of excrement from animals living on top of the soil, and how it breaks down and adds various chemical components to the soil, and are included in the litter and organic matter that's gradually sinking into the soil. But also animals digging and nesting activities, the role of worms, earthworms, in their activities of producing worm castings that are basically a very beautiful, pure form of humus. So a form of humification that is, again, essential for soil building. And then animals that, like worms, crawl through the soil, create an aeration of the soil, so that actually the soil is optimally being mixed, again, for the root penetration, for water absorption, for deeper penetration of organic matter and carbon. Now, how do we use those principles? We use them, and I mentioned that in the first webinar, in monitoring through observation and analysis. We did a bunch of simple tests, and we do that through monitoring, for instance, with the use of the Bullseye method, which I like very much, but there are many other monitoring techniques that are typically much more scientific and quantitative, and that in different environments might be really important, such as scientific research environments. But for practical management, this is a very good bridging tool that's based on science, but has a qualitative output that helps direct, through a rapid appraisal approach, the decision making. And then we have management practices. We're going to touch on that a little bit, and then in the next webinar, really delve into that. So if there are any questions at this point, I can entertain for about 5 minutes before we go on to the monitoring component. If you have questions, please put them in the chat, and then I will see if I can answer them. And if there are no
I can pull from the chat. I have one kind of a broad question here from the beginning part of the webinar. So yeah, Rich Schrader wanted to know, and this is just kind of a general question here, but how could the Freedom Ranch approach that we've been talking about be applied in the context of Forest Service lands with projects like the Forest Mayor Domo project that involves the Cerro Negro Association? That's mm-hmm. You're aware of that project? Okay.
Yes. I think it can be applied really well in understanding that, for instance, there are different types of pinyon juniper, and that they need to be treated differently based on their fire cycles, water holding capacity, capacity to grow grass or not. And for instance, that if you start thinning for firewood in pinyon juniper areas that have a lower capacity to grow grass, that you probably invite over time more erosion there. And if you do that, or have done that, what are then the techniques for reducing that erosion and still covering the ground to optimize grass regeneration, for instance? And we're going to get into that. So that's one approach. So another one would be to apply the monitoring techniques, especially through the Bullseye method for forest and woodlands that I have converted from Kurgadzia's approach. And so that is an approach that I think is just very good for the Mayor Domo type of woodland management.
Rich has a follow-up question here. Was it possible that the Freedom Ranch had a lot more grassland in the past? And even though the fire cycle isn't quick in the PJ forest, or isn't on a low and fast return interval, I guess is in the PJ forest.
I believe that it actually did have more grass. From the experiences of thinning and mastication there, we've seen that in many places grasses have come up. As I mentioned also in the pinyon juniper review and their soil types, there are many areas where there is a fine textured soil of loam and clay, and they are actually good for grass regeneration. So there might have been much more grass. On the rockier sites, we might actually have seen just more, you could say, persistent old growth type of PJ, but we don't know yet. And the moisture regimes have changed over time. There has been much more erosion over the last 100 years. So it may also be that just in the land use history over the last 150 years, you could say there might have been a shift away from more persistent woodlands and ponderosa pine, which might have been there much more predominantly, to an open savanna landscape where grass is more dominant.
That makes sense. Let's see here. I have some more questions here. For the sea sequestration, the sea layer, what is better, grassland or forest or savanna?
Oh, that's a very a question that I love. It is not quite clear yet. I think the how would you say that the science has not really indicated that yet. There are indications, there are early indications that actually grasslands are very good optimal carbon sequestration ecosystems. However, they don't go as deep as pinon and juniper woodlands. And the more recent research indicates that persistent woodlands, because of the depth and the lack of fire, may actually be more effective carbon sequestration ecosystems than the grasslands. Also because more than 55% of our entire forest landscape and is pinon juniper in the West, they are forming such an important ecosystem that actually just by their mere size of area, they are very important in storing carbon, and therefore they should not be underestimated. It is more our land use history in the pinon juniper and prescribed fire and all kinds of things that have happened that have muddied the waters in the importance of pinon juniper as a carbon sink.
Mm-hmm. Okay, thank you. I have one more question here in the chat.
Okay, let's do one and then I need to move on.
Excellent. Okay, Carmen Rose would like to know if you could provide additional information about how organic matter could be incorporated into degraded PJ soils, and which inputs, such as biosolids, biochar, manure, compost, etc., appear to be the most beneficial in increasing soil health.
Oh boy, that's a difficult question and probably requires a long answer too.
Mm-hmm.
First of all, I'm not quite sure of any comparative research, and I've not done any myself, of course. So that is hard to answer based on my personal experience. And like in so many of those situations, it matters. Just as we're learning about the variability of the pinon juniper ecosystems and our soils, I think we're still in a phase of learning about these ecosystems in ways that we need to experiment and try multiple solutions and see what works best in each environment and condition that we're working in. And maybe that is the quickest, wisest answer I can give right now.
Yeah.
But I would love to entertain that question a little longer, maybe by email or something offline here.
Mm-hmm.
So let's move on. But thank you for the questions. That's wonderful.
Okay, thank you.
So we're going to look at erosion and soil loss. So to define erosion, I came up just with a very loose but focused one, and that is that erosion is the process of loosening and the removal of soil components, the organic matter, the mineral litter, everything of soil that is being removed. And that can be the topsoil or the deeper organic and mineral matter. Then the result of that erosion is the soil loss. Often these two terms, soil loss and erosion, are used interchangeable, but that's not quite correct. Soil loss is the result of the erosion that you measure as what you basically have lost, the disappearance of that soil. So how do we know that we actually have erosion or that we're having experienced a loss of soil? Well, the first sign is that we have bare dirt patches and that these patches are connected. And I'll explain why that is a sign in a little bit with some images. And that we have plant pedestalling. That means that plants are standing on a little stool, you could say, of their roots or their root crown and a root collar, and that the soil around them has actually washed away. That's not natural. You see that so much that a lot of people think, oh, that's just a bunch grass. It needs to be bunched up. No, actually soil needs to be flush with the root crown, the root collar of a plant, and you shouldn't see that above ground. Then you have desert pavement, which is a gravel cover of which all the fine particles have been removed. And in desert pavements, you see very few plants. Then you have enlarged microtopography, meaning basically rills, gullies, and much more up and down terrain. And then finally, patches of sediment. And the sediment by itself is a sign that there was erosion and soil loss somewhere higher up. And that can be in the form of mounds or fans or just blankets of sediment. So this is what it looks like. Erosion features are, for instance, crusting. And maybe all seen that, and that's when soil at the top is very fine in texture. It's silt or clay that has been removed from the soil structure, the soil matrix, by a raindrop splash. What it means is that a raindrop falls down and its energy dislodges the top half inch or so of the soil. And because the finer particles like clay and silt are lighter, they are more energized and jump higher. So you get a layering eventually of the soil where actually the finer particles come down, fall down after the splash effect, and the splash can go up, as you know, if you have walked through a rain area, it can go up to your knees sometimes, that you get splashed by whatever splashes up from the ground. And so it starts to dislodge and move those fine particles. They form then a layer on top of the coarser particles of sand and gravel, and that eventually dries out more quickly, the top layer, and then once it dries, starts to crack. And that's what you're seeing here. What you're starting to see there too is the pedestalling, right? Especially visible also in some of the other pictures here, where grasses, but also clumps of biocrust are elevated above that crusty soil. And because all the soil around it has splashed or washed away, and that washing away of the topsoil when consolidated masses of water of maybe 1/10 of an inch, 1/4 inch, or a full inch wash down a slight slope is called sheet erosion. And that then removes those fine particles. It might seal off the topsoil as in the bottom left picture, but then the plants or biocrusts are sticking up a couple of inches. And that's a very clear sign that you've had sheet erosion and that you have crusting and pedestalling. Then in the top middle picture, you see desert pavement, where all the fine material really has been removed, partly by water, but largely by wind. Because once this dries out and these fine particles are just at the top of the soil, they're readily available by wind to be picked up and removed. And so At this point, probably 3 times more of our fine particles in New Mexico from pasture land is removed by wind than by water. An NRCS estimate is in the order of 14 to 15 tons per acre of pasture land per year in New Mexico that's removed by wind, in comparison to 4.5 to 5 tons per acre per year in pasture land removed by water. At the bottom right, you see examples of the pedestalling and the connectedness of these bare grounds as a result of sheet erosion, where that bunch grass, blue grama here, is really elevated a couple of inches above the landscape, above the soil top. And then the soil blanketing, where actually you see a covering of unsorted fine material that is covering plants, that is covering organic matter of little sticks and twigs and pebbles. And that is another sign that you had erosion higher up. So another couple of erosion features that are not so subtle are those of mass removal. Rill erosion, where actually slope increases a little bit, where water concentration increases, and where you then get concentrated flows. And if they get really big, they turn into gullies. Rills are still theoretically removable by hand or with a plow. Gullies are not. They require heavier treatment. And then gullies also by themselves erode again in the form of bank erosion. Other forms are then sedimentation in the form of alluvial floodplains, where you have large-scale sediment depositions on floodplains or in the arroyo bottoms themselves. Examples of scouring by vehicles or tires or sometimes animals that lead then to basically the removal of that topsoil layer. In this picture, you can't see it because of the contrast, but this off-road vehicle track is about 3-4 inches deeper and then scoured further by water, or a combination of everything, where you have both alluvial fans, but then erosion as a result of water and tracks breaking through those alluvial fans, etc. Now, I want to explain about the Bullseye method. I had a little video, but I got feedback from people from the first webinar that the videos weren't usable. So I'm actually going to just voice over this little thing. So monitoring on Glorieta Freedom Ranch has been done, like I said, for about 10 years. And in the last couple of years, we've begun using the Bullseye method, which hopefully helps to come to quicker management recommendations. The Bullseye method was developed for rangelands by Kurt Gadzia and Todd Graham about 15 years ago. I adapted that under a contract with Santa Fe County for the use in forests and woodlands. And the method is using a simple Bullseye target and target sheet on which you can collect the data, and is guided by a forest and woodland scoring guide. And I will go through them right now and have a little exercise. So the Bullseye method is, it tracks changes over time, over many years, and that is basically monitoring, which is tracking progress and seeking early warning signals of desired and undesired change so that you can act on it in terms of management. The Bullseye method is a hands-on tool for those working directly with and on the land. It's a solution that isn't on the scale between no monitoring at all and of scientific, technical, detailed, qualitative monitoring. It's practical, science-based, as I said, qualitative, and it's a rapid appraisal approach. It can be used in combination with qualitative monitoring, and it actually also is very helpful to use it in combination with pictures, and we'll do that a lot here. It's interactive, so you can be doing it in a small group, and actually it's very beneficial if you do it in a small group as a form of collaborative learning and decision making. And therefore it's very good for community members to implement techniques, teach each other, etc. Like in response to the question of Rich Schrader in regards to the Mayordomo system. So let's begin with this Bullseye method. Let's see, the Bullseye method begins with actually jotting down landowner goals and the desired conditions for the forest or the rangeland. And then you document the current conditions, go through the scoring method to fill out the Bullseye form. And then from there in the right-hand column, you can actually already jot down ideas on what you might want to do in terms of land management. And because the Bullseye method looks at above ground and a little bit of the topsoil elements, it's an excellent method too to actually use at soil health to identify soil health conditions. So now look at this landscape, and through this chat box you can send observations in relation to various qualifiers or indicators in terms of soil cover. See soil cover. Is it good or not? Is it desirable or not? Plant distribution, tree age, etc. I'll go through it right now. So here's the list. And each of those pictures had an above ground shot and a downward looking shot, of course, in the same location, so you have a better idea of what's on the ground. So the Bullseye method looks at understory cover and looks at if it's very good, meaning gold, and that means you're achieving your goal. For instance, for understory cover, you look at the amount of understory cover and whether that nearly or totally matches that is expected or desired. Well, it's a vague description, but you can actually, in background literature or based on reference conditions that you have to research for the site, identify what is desired or to be expected. The silver category is that you're moving toward or away from the goal, dependent on what the previous condition was, if you do a sequence of monitoring in this way. And so that asks, is the amount of understory cover lower than expected or desired for the site? And you would have bare areas. Bronze means, and that's the lowest level of achievement, that you're actually not achieving your goal and that the understory cover is much lower than expected or desired, and that there are many large connected bare areas. The second is the presence of topsoil, or basically a lack of erosion. If there's little to no evidence of erosion, so no presence of topsoil visible or bare ground, it's very good, right? Or if there's no desert pavement, no pedestaling, no rills or gullies. If there's some of that, you're in the silver, and if there's quite a lot of that, you're in the bronze. And so it goes on for all the different categories, like the amount of litter and duff, dead and decadent herbaceous material, and fine fuels. So for instance, if there's a lot of brown, white, blackish plant material, it means that there's a lot of dead and decadent plant material. In some cases, that might be good as a mulch. If there is too much of it, then you may actually have a fire hazard. And it depends really on the perspective of the land manager, what you actually fill out here. And that has, again, to do with the goals of the landscape. And if you have, for instance, a home nearby, then the fuel component in evaluating this may be much more of a concern than if you're going after, say, wildlife habitat or biodiversity. The amount of medium and coarse fuels is an interesting one, because thinking back, for instance, at the wood fuel co-op, a certain amount might actually be nice because then you have a wood fuel source. But for, say, wildlife habitat, it may be not so good, or in relation to wildfire management. Litter and fuels distribution is another one, and we're looking particularly here at finer fuels. Then the presence of soil life and soil moisture, and therefore you actually have to have a probe or dig a little soil pit. And we are being asked there to find abundant signs, or moderate signs, or no signs. Then the percent desired plants, greater than 66% is desired, then you're in the gold. 33 to 66%, you're in silver, or less than 33%, you're in the bronze. And then tree species richness and function. Do these trees or shrubs provide cover, shelter, diverse habitat? Those are functions identified or given by the different species and their age classes, etc., and their distribution. So if you're doing well on that, you're in the gold, and not so good, then you're maybe in the silver and the bronze. So let me play this video, and that it's very brief. I think I did what I need to do, share, and then we can listen about what I found in the soil. This clump of soil indicates various signs of biological activity. We have an insect here, small carcasses of insects there as well. On the soil were also several pellets from animals, and the soil hangs really well together through roots and what I suspect is mycelium. There's another little insect right there, another one that just crawled away. So this soil is pretty deep and full of life. So a small soil pit up to 1 or 2 feet really helps with seeing what's in the soil. And you might also find little glomalin balls or little balls of dirt that are hanging together by mycelium and exudates from the mycorrhizal fungi. It indicates very high soil structure and soil biological activity as a result of the mycelium in the soil. So that soil is full of life. Well, looking at the other criteria here, there are age and diversity of desired tree species, tree health and vigor, ladder fuels, tree stem density, tree canopy cover, understory vigor and function, user and emergency access, and the presence of living organisms. So what did we find? Did we get any feedback on what people saw on this landscape? Well, as you can see, I scored it really high. I think that the understory cover was relatively quite good. It was not ideal yet, but it's definitely going in a good direction. There is a good amount of litter, and there is, from a fuels perspective, maybe not a good amount, because maybe almost too much. I skipped the presence of topsoil and lack of erosion. That's still very good. Here and there was some erosion. That's why I put it in the low gold, but in principle, it's a good site in that regard. The amount of medium to coarse fuels, number 4. A lot of dead and down, almost a little too much, and maybe definitely too much from a fire perspective. Then the distribution of that litter and fuel, well, that was pretty patchy, and it's here and there stored under trees, which is definitely a fire hazard. And also the distribution is here and there even too thick for proper plant regeneration and nitrogen retention in the soil. The presence of soil life and soil moisture we saw from the soil pit was very good. Plants, desirable plants percentage is actually very good. Tree species richness and function is not great, although it's fine for this ecosystem, but it's been cut in. And so I put it in the low gold, but all the necessary species were in the immediate environment, but they were a little sparsely represented. And that also was a problem with age diversity. It was messed up because of some historic cutting that took place there. Tree health and vigor was generally okay. Some species had mistletoe, and the vigor was somewhat affected by drought. Ladder fuels and crown height was definitely an issue. It was not an extreme issue because the crown height on pinyon juniper is typically pretty low from the ground up to maybe 4 or 5 feet. And you cannot compare that with crown height in ponderosa pine that should be more 15 to 20 feet or more. So it is in that sense a flammable environment if there is a ground fire that might jump into a tree. Stem density was relatively low. Although if you see the grass regeneration, then you can also say like, oh, maybe it is actually pretty good because we're moving towards somewhat of a savanna or open woodland situation with grass. So that is a debatable topic depending on your management objective or scientific way of looking at it. And tree canopy cover falls in the same category. I think it is really low there. Also, the problem is that the clumps of pinyon juniper that are really important in terms of their clumping structure have been affected. So that is not quite ideal yet. But as it regenerates, it might go in the right direction. Tree canopy cover, we just talked about that. Understory, vigor and function is, as I said, also affected and needs to restore itself. Accessibility is very good. It's just 100 feet from a road, and the presence of living organisms is very good as well. Now, this is interesting because we did this Bullseye method before. And so here you can appreciate the differences between what we found last fall and this summer when I prepared for the webinar. And you see some differences, right? That last fall we scored this a little lower, and over the last 9 months it has improved, or 7 months, it has improved a little. That is probably because of some moisture and just regeneration of the site. And it might be just seasonal effect and some interpretation between observers. Although I did this this year by myself. Last year, I did it with a partner in this work. And so we came to a slightly different observation. But the overall tendency that you see is that it's the same, that litter and fuel distribution is a problem, and that understory vigor and function and tree canopy cover is maybe still also not that great, but it's maybe moving in a desired condition. So that leads me then to discussing the soil loss estimation, because you can add a quantitative method to this, which is based on the revised universal soil loss equation, where soil loss is a function of rainfall intensity, R, and soil cover indicators, C, soil erodibility, K, and slope factor, based on the slope angle and slope length. We use a standard rainfall intensity value for this area based on what's given nationwide for each county, based on elevation and rainfall curves for the area. For this area, it's 45.796. And you can actually back up a lot of the data by also looking it up in tables, or enter the data into tables given in a publication by Dunn and Leopold that directly uses the basic information from the NRCS developed by Wishmeyer and Smith in the 1970s. And it gives a very detailed way of approaching soil loss, much more detailed than the web soil survey provides for larger soil complexes in this landscape. And you can use, for instance, modeled approaches like the EPA's Steppel method to calculate these kind of things as well. I do this by using 1 square yard plots along transect. We walk along a transect and that impacts the soil. So I put my quadrat plots 3 feet away on either side, staggered from the transect line, so that we have minimal impact from walking along the transect. And that actually that really optimizes your data set. So what we're seeing here is what I found on the ground, right? High amount of plant litter, some surface stones, a deep, more than 6 inches deep, active organic matter horizon, very good soil structure, many small clots. So the soil is very alive here. Then we found 0 bare ground, 15% grass, little less than 1% of forbs, /10%, 65% litter, and then 75% trees over 7 feet. You can enter all those things in a table and or in in nomograms and compare them in different tables in, for instance, Dunn and Leopold.
Excuse me. It did cut in. I don't know if that's happened just for me, but
I need to repeat it again because was it choppy?
just for 1 second.
Okay.
Maybe just a bit of that slide.
So yeah, so what you need to do is enter these data into tables or nomograms that are given in the document by Dunn and Leopold or in the Steppel documentation, the Steppel model of EPA. And then you can start to calculate the different indicators in the Russell method, in the revised universal soil loss equation. So we found 4% organic matter by just a rough estimate. If you want to do this right, you have to send it to a lab. But I make just a rough estimate based on what I found and based on how to interpret this from using literature as to how to interpret the organic matter component. But that's somewhat subjective. The permeability is very high. Stoniness is present at the surface, and that leads to a somewhat modified interpretation in the web soil survey of the K factor. So doing this after 10 plots, we came up with averages. And and then the slope, I need to mention that. We look at slope that is uninterrupted by logs or vegetation, very much along the intent of the initial soil loss estimates that were done in a field with plow furrows up and down, so not horizontal along contour, but straight down. So that means that actually, if in a rangeland situation like this, the water flow is interrupted, then you basically end your slope length. So that led then to specific findings. You enter that into the formulas and you calculate your soil loss. For this site, it was very low, 0.022 tons per acre per year. And I compared that with the tolerance factor, which is a factor given by the NRCS as to what the soil development capacity is. And that is 1 ton per acre per year in this location for this soil type. So we're staying way below the natural soil accumulation, the soil formation, the natural soil build-up capacity of this soil if it were in a healthy situation. So because most soils in New Mexico are compromised, they don't meet that T that is given by the NRCS. So you have to be really careful to use that as a standard. But because this soil is so healthy, I think it is a fair comparison to use here. That leads then to possible management practices. And I'm seeing that I'm out of time, but we're going to come back to this the next time in the next webinar. But I want to just identify that in the web soil survey, we have fine and coarse fuel loads that were a problem, soil cover and erosion concerns, uneven litter and fuel distribution, age class distribution, ladder fuels, low stem densities, and low canopy covers. And then you can identify maybe why they have occurred. And I've mentioned those before, right? Because of tree removal by wood cutting, for instance, and uneven litter distribution as a result of the wood cutting. Then you can start looking at what the possible solutions are. Well, for this site, looking at slash redistribution, and then maybe starting to consider a small-scale prescribed fire would be one of the options. And there are, of course, pros and cons of each of the options that you might want to consider. In some of these cases, like low stem density and low canopy cover, waiting and monitoring might be just the best option. And that leads then to an identification of the work needed. And those 4 categories in these columns are the ones that are from the worksheet in the Bullseye method. So this is how you go then about identifying your management measures for the next steps. What I wanted to do too, but I think I need to postpone that to the next webinar, is to look at grasslands where you have very similar categories. And these are original from Kurt Gatzia and Todd Graham out of their booklet, Bullseye, Targeting Your Rangeland Health Objectives. And you go then through the same kind of exercise, looking at a grassland, looking at ground cover, looking at bare ground, plant diversity and functionality, biological activity, etc. And that leads then to the same way of filling out the target. In this case, we found much more bare ground, as you can see in the pictures, more signs of erosion, more plant pedisoling, poor distribution of litter and medium-low litter amount, and so on, poor litter incorporation. The best factors were basically the amount of living organisms, but everything in this grassland was suboptimal. And that leads then to the same way of listing the problems and the possible causes, which in this case have to do with past erosion, past land use, past grazing, rutting as a result of maybe a track that was there, and maybe even too much resting right now, so that you actually might invite some animals out there to graze, to disturb the soil, redistribute the litter that's dead standing, and then get some more biological activity going with the hooves working that into the soil. Also, what you might want to do here is masticate and thin the juniper and pinon trees that have encroached, have a managed grazing plan, conduct some erosion control measures, and then bring that grassland up to health, like we've done in other places on the Glorieta Freedom Range. And that leads me then to the end. And if you have time, and if Gabe has time, maybe I can address a couple of questions, and otherwise we can do that maybe by email.
Yeah, I'd love to field some questions if the group has any questions or comments that they'd like to share. Let's see here. See if we get some coming in. I find this Bullseye method, speaking for myself here, a really valuable tool for, like being able to get groups of people to kind of work from a common framework for managing multiple goals, or kind of from different management objectives at the same time. I've been working with soil and water conservation districts a little bit in the East Mountains area, and as part of their cost share program, they're interested in some kind of simple monitoring methods that would be usable by landowners, and this seems like it would be a very valuable tool for something like that.
Yeah, thank you for bringing that up, because the booklet itself goes way beyond just the forms that I've shown. It actually gives the entire background in soil health and terrestrial vegetation health for instance, grazing purposes and stability and resilience of grasslands. And then it actually has various other forms in the back that help you with documenting plants and that help with documenting management measures. Mm-hmm. And because you can do it as a group standing together and making joint observations, you eventually come to a pretty balanced perspective. Mm-hmm. And then doing that again a year later together, then you can actually compare notes again, see how certain conditions have changed. And that's very encouraging because you have a dialogue, you mm-hmm. learn from each other, and you can see over time how the conditions have changed and how you maybe have responded to certain management measures that you have taken as a result of your joint monitoring a year before. So mm-hmm. again, also in relation to Rich's comment earlier, I think this would be a very helpful method for the Mayordomo project.
Mm-hmm, mm-hmm. Yeah, I agree.
Kirkazia has applied this method throughout his career from Hawaii to New Mexico, and Quivira Coalition has been teaching it. The document is available on the Quivira Coalition website.
Great. I'd love to pass this along to our partner down in Ciudad Soil and Water Conservation District. I think they'd really appreciate it. And I also like that it kind of looks at everything in terms of trade-offs among different management objectives instead of kind of, just taking one perspective and just managing from that one objective, like, fuel reduction, for example. But also just kind of looking at the whole picture there, I think is really effective. Brad wanted to know if this was originally designed for the five soil health goals were originally designed for the plains of Iowa. That's
well, I think it actually was designed for multiple different soils. It was definitely designed more for agricultural lands than for pinon juniper woodlands. And I took really a leap of faith to propose to the state to have a soil health series of workshops, which became webinars on the soil health in pinon juniper woodlands. Also arguing that pinon juniper woodlands are old agricultural lands with pinon nut harvesting, firewood harvesting, and grazing in New Mexico. And that many of them have very deep, healthy soils, which we have seen here. And so they definitely, obviously, were supportive of that idea. And I think that actually, besides maybe the topic on minimal disturbance and external inputs, which really is for croplands mostly, that all the soil health principles apply to rangelands and woodlands very well as well. But like I mentioned in the previous webinar too, I think that the soil health principles focus so much on the biological aspect of soil, not on the hydrological or mineralogical or whatever, because we have really lost sight of that in our agricultural methods by replacing the biological, the biosphere with our engineering, our agro-engineering components.
Some questions coming in here now. Isabella, I might mess up your last name, Janishes, says, would you use planned grazing to restore soil health in PJ woodlands?
Oh, thank you, Isabel. Yes. So that is definitely on the list, and we're going to talk about that in the next webinar. So planned grazing is part of the toolbox and is part of the toolbox of Glorieta Freedom Ranch, and we're working on a planned grazing plan as we speak with the NRCS to get that going. And so especially when you have a grass cover and don't want to use fire in a lot of the situations, managed grazing is a very important tool. It's also a natural tool. We have natural ungulates, especially deer, maybe an occasional elk, and of course ants, and who are not ungulates but plant eaters, and rabbits in this landscape. And so the foraging and the eating of the grass component is an important disturbance factor that needs to be maintained. If you don't do that, you actually deplete the mineral cycling by having dead plant matter of grass and forbs standing there without it being trampled on the soil as a mulch and worked into the soil by the hooves and by smaller animals. So for optimal mineral cycling and soil structure improvement, grazing is very important. But of course, it has to be managed and planned so that you don't overdo it, because animals are habitual and they like to eat what is most palatable. And so you have to spread them out over time and space so that we manage that land in an optimal way all over the place.
Cool, we got one more here. Rich wants to know, kind of how much the hydrologic connectivity down the fall line of PJ forests, particularly where high sheet flow has created funding. How much does it contribute to the soils in New Mexico PJ forests?
Oops, there was a little blip. Okay. So can you summarize it again?
Yeah, so we're wondering how is the hydrologic connectivity on the fall line of dense PJ forests, particularly where these forests have a high sheet flow and have mounding. How much has that contributed to the decline of soils in New Mexico's pinyon juniper forests?
Well, thank you for that question, Rich. I think it has happened a lot in areas that had high grazing or high disturbance, especially on soils that were sloped and were disturbed and had fine textured soils. So old working land, PJ forests, definitely had that problem, that openings in the forests that were overgrazed started to show bare dirt, and that then water carried that dirt down on fall lines, meaning straight down the slope, and that led to depletion of soils higher up and accumulation of sediment down in sometimes irregular patterns. And then you get all kind of factors of flooding, alluvial fans that then change the vegetation lower down, but also higher up. For instance, higher up, you might get really depleted pinyon juniper woodlands because there is not a lot of topsoil. What you also get is then that there's not enough grass growth, so that actually you don't continue more frequent grass-fed fires, except for when you had permanent woodlands that didn't grow a lot of grass. So we have changed the ecosystem as a result of that. And there are even signs that there were areas, probably here around Santa Fe and all around the Sangre de Cristo Mountains, where we originally had ponderosa pines 200-300 years ago, where the ponderosas burned, where then with the Spanish occupation and the American occupation later, grazing took place or homesteading on these old ponderosa sites that then didn't grow the ponderosas back because the land was cleared. And then you get that occasional pinyon juniper was brought in, but cut or burnt again. That grazing didn't provide enough low intensity fires, high frequency. So you got actually either very high intensity, infrequent fires in the ponderosa and pinyon juniper that cleared even more land, or you got that after a certain period, like after the 1950s, when the grazing boom ended, that a lot of PJ grew back, and that we actually see kind of depleted poor PJ areas in areas that were prior disturbed, and that actually now need some opening to see if we can get grass to grow back. So it's a very complex layering that we're gradually discovering that happened in these different PJ areas.
Mm-hmm. I have a couple more questions here. Susan Osley is interested in how much emphasis is put on invasive plants in your monitoring method here.
Fortunately, we haven't seen a lot of invasive plants, but we're definitely looking out for invasive plants and any form of exotics that are undesirable. So now that we've had some mastication, I will be looking out for cheatgrass, for instance, and thistles. And so, and they are common to occur after those kind of treatments. Fire has that effect as well. And that is definitely a concern. There are experimental and research papers that show that over time, native plant cover may eventually take the upper hand again, but that in the first several years, the growth of invasive plants could definitely be an issue of concern after such kind of treatments. And therefore you have to, I think, treat small areas at a time, keep monitoring, and take timely measures so that they don't start spreading to areas that have not been treated but have been disturbed in other ways.
Thank you. Rich Schrader is interested in, where in your soil schematics would you indicate areas where low-hanging, areas where some work done, interventions. So, where hanging fruit for intervention?
Low-hanging fruit for interventions. I think the low-hanging fruit for interventions, and we've been working through that with Brad and Kathy, are those areas where, for instance, we can remove pinon and juniper in those grassland areas where they have encroached on the grasslands and where they're replacing areas where grass could naturally grow better and stay longer, even through drought seasons. And where you can then cut and create slash, full lop and scatter or masticated chips that you can spread to the open eroded areas, and where you can also then use the stems as pickets for small erosion control structures like wicker weirs, and the boughs of Rocky Mountain juniper that are really pliable to weave into those structures so that you capture the runoff and the sediment that's coming down with it from these eroded grassland areas, fill up those tracks and gullies, and then eventually heal the grasslands because they're more level, the water will be more distributed and spread out, more supportive of grass rather than just hardy forbs. And so I think that is a good method of a low-hanging fruit where you can start. Then in terms of the denser pinon juniper areas, it depends really on what your objectives are. And so we're still looking at those areas, and the objectives, of course, here are in part fire risk mitigation, but also identifying those areas where grass can naturally grow and provide a better cover to soil than maybe scraggly pinon juniper. So where the pinon juniper is healthy, we of course want to maintain that pinon juniper landscape. Where it's not, you need to start looking at the soil texture and the soil structure to see if actually grass might actually grow there, and then do some treatment that creates just more cover and greater diversity.
Mm-hmm. I think that's the questions that we have right now in the chat for you, Jan Willem.
Well, thank you very much, everybody, and thank you, Gabe, for moderating this session. And I apologize for those who had to wait longer for me to finish. I had clearly more to tell than I anticipated. That seems to be a problem for me. Anyway, thank you very much for hanging in there. Please also think about the next